In this video, I'm going to introduce you to elimination reactions. So in the last chapter, we talked about substitution reactions, and we saw that if we were to take an alcohol like the one in front of you and react it with a strong acid with a nucleophilic conjugate base, then we could get a substitution reaction, because what would happen is that our alcohol is weakly basic and is therefore able to deprotonate the strong acid. That gives us this protonated intermediate here. And then in this case, we're looking at a tertiary alcohol, and therefore the leaving group is able to leave on its own, leaving behind a tertiary carbocation. And then that, of course, is a highly reactive electrophile, and we have a really good nucleophile in the mix in our bromide. And so the bromide is able to attack that positively charged carbocation and give us the resulting alkyl halide as a substitution product. And this is, of course, an SN1 reaction. But what if our strong acid didn't have a nucleophilic conjugate base? What if instead of using hydrobromic acid, we used something like sulfuric acid? Because hydrogen sulfate, HSO4-, is not nucleophilic at all. Well, our reaction is going to start off the same way. Our tert-butanol is still a weak base. So I'm just going to redraw out my tert-butanol here. We still have a strong acid. It's just that our strong acid is sulfuric acid instead of hydrobromic acid. I will draw out the full structure of sulfuric acid up here, but remember that I have told you that if you want to abbreviate it, this is the best way to do so because it preserves all of the important information, the hydrogen-oxygen bond, and the oxygen becoming an anion after it's deprotonated. So in this case, we can take our lone pair on our oxygen, reach over, grab the acidic hydrogen, kick out the conjugate base. This is exactly the same step as it was in the example at the top of the slide. And so that's going to give us exactly the same protonated intermediate. My oxygen now has 2 hydrogen atoms attached. And of course, I generated the conjugate base of my sulfuric acid. Now, this is, of course, such a stable conjugate base because of all the resonance stabilization of that negative charge. It's shared by all 3 of the oxygen atoms that don't have hydrogen attached. So we've generated the same protonated intermediate as in the top example. And just as in the top example, we can have water leave as a leaving group in order to give us a tertiary carbocation. And as carbocations go, tertiary is a pretty good choice. And we have also then kicked out a water molecule. So we've made an extremely electrophilic carbon atom in that tertiary carbocation. If we look at what is in our flask that could feasibly function as a nucleophile, we can look at the hydrogen sulfate over here, but it's not nucleophilic, so that's no good. We can look at the water over here. It's not a good nucleophile, but it's somewhat nucleophilic, and we could arguably have the lone pair on oxygen come in and attack that carbon cation, but all that does is take us back to the last step of the mechanism. So it's viable, but it doesn't do anything. So we need to think about what else could happen. Yes, this arrow here should really be an equilibrium arrow. And I suppose arguably this arrow here should really be an equilibrium arrow. But if our reaction is going to progress forward, what else can happen? And to do that, to see that, I'm going to have to take one of these methyl groups and actually draw out all 3 of the CH bonds. The other thing that can happen is that instead of acting as a weak nucleophile and directly attacking the carbocation, the water can act as a weak base and deprotonate the carbon next to the carbocation, forming a new carbon-carbon pi bond. And that will give us a double bond where we just removed the hydrogen from. And then these two methyl groups are still here. And of course, we have generated H3O plus as well. This is an elimination reaction. It can happen under very similar conditions to the substitution reaction. And when we think about substitutions, we tend to have to think about eliminations alongside them as a potential competing reaction. Similarly, when we look at eliminations, we're going to have to remember that substitutions are a potential competing reaction, because oftentimes the conditions that are conducive to one type of reaction are conducive to the other as well. As you can see here, there are a lot of similarities in the mechanisms. It's not only SN1 reactions that compete with elimination reactions, SN2 reactions do as well. We can imagine that we might want to do an SN2 reaction between ethoxide and 2-bromobutane by having the negatively charged oxygen atom come in and attack that carbon directly, kicking out bromide. And that's certainly one thing that can happen if you mix ethoxide and 2-bromobutane. But it's not the only thing that can happen. Our ethoxide can also act as a base. So we still have our ethoxide here, and we still have our 2-bromobutane, and I'm just going to draw out all the atoms in it so that we can see what's going on. Don't forget the lone pairs on the bromine atom. And so option A, of course, was the substitution where the oxygen comes in directly, kicks out the bromide, but that's not the only thing that can happen here. The other thing that can happen is that the oxygen can reach down and grab a hydrogen, again from the carbon next to the electrophilic carbon, and we'll see the official term for that in a few pages, and create a new pi bond, kicking out the leaving group. And so if we follow those arrows, then what we have now constructed is, of course, ethanol, because we protonated the ethoxide. And for our main component of the reaction, we have just made a carbon-carbon double bond there, where we used to have a single bond. The bromine is no longer attached to that carbon. And there's a methyl group there, and another hydrogen there. And of course, I've drawn the cis isomer there, but I could just as easily have drawn the trans isomer. And then I should also draw my leaving group. We also have generated a bromide ion. So you'll notice that in both of these reactions, we created a new pi bond. So here it is on this example, and here it is on this example. Also, in both reactions, we lost a small molecule. In this case, it was our water, and then the hydrogen atom, one of the hydrogen atoms on the carbon next to the carbon that had the water attached, and possibly easier to see in this example because I can highlight them in the same picture. Here we lost a bromide ion and a hydrogen on the next carbon over, creating effectively HBr. Notice that the two pieces of small molecule that are eliminated are coming off of neighboring carbons, and the new pi bond is between those two neighboring carbons. So make sure that you're removing the hydrogen and the leaving group from adjacent carbons. You'll notice that the terminology for elimination reactions mirrors the terminology that we used for substitution reactions. The elimination reaction that went by way of a carbocation intermediate, in which the leaving group left first, so there was only one molecule involved in the step in which the leaving group leaves. It's called E1. E for elimination, 1 for one molecule in the rate determining step. And so it, therefore, is a first order reaction, just as the SN1 is a first order reaction. And so if we want to write the rate law for an E1 reaction, It is therefore going to have its rate equal to some rate constant times the concentration of your substrate, this concentration of the molecule which contains the leaving group, which I will abbreviate here as Rx. And the reason that it is first order is because there is an invisible exponent number 1 up there, which we don't typically draw. Similarly, in my second example, you saw that the base attacked the substrate directly, kicking out the leaving group directly, so those 2 molecules had to collide in the rate determining step of the reaction. So that is an E2 reaction. E for elimination, 2 for 2 molecules colliding in the rate determining step, analogous to an SN2 reaction. And just as an SN2 reaction is second order, an E2 reaction is also second order. And if we wanted to write the rate law for it, we would have its rate equal to some rate constant times the concentration of the substrate, the material that has the leaving group in it, and also times the concentration of the base. Again, we have these invisible exponent 1s that we don't normally write. Add those up, you get a total of 2 in the exponents, and that is why this reaction is second order. We'll talk about both the E1 and the E2 mechanism in more detail, but recognize that we're going to be looking for similar factors in terms of choosing between E1 and E2 that we looked at for SN1 versus SN2. For an E1 reaction, we have to make a carbocation, so we're going to care about its carbocation stability. For an E2 reaction, we have to use the base to push the leaving group out, so we're going to need a really strong base.